Last day we were looking at resonance structures that bopped back and forth between 2 or 3 different structures. Now, in reality, what we discovered is that the bonds were never, like the bond was never actually a single bond, and it was never actually a double bond, because the bond length is actually halfway between the length of a single bond and the length of a double bond. This is page 118. Is this 118? Yeah, 118. So it's not like it's a single bond some of the time and it's a double bond some of the time. What it really is, it's like if you have yellow and blue and you mix them together, you don't get yellow, blue, yellow, blue, yellow, blue. You don't get like stripes. You get green. Okay? So if we have resonance structure A and resonance structure B, and we mix those two together, we get an ozone molecule. This is a space-filling model of an ozone molecule that looks identical from one side to the other. Okay? And we can kind of, and let's see if they've drawn it here anywhere. You can kind of represent this as an O with a single bond here and a single bond here and an O and an O. But this second bond is those 2 electrons in that bond are spread out over 2 areas. These 2 electrons are spread out over 2 areas. So instead of having a single bond and a double bond, what we really have is a 1.5 bond and a 1.5 bond. Okay, so if we redraw this again here, that's a 1.5 bond and a 1.5 bond rather than a single and a double. Okay? Now, what if we had like nitrate? Or actually, never mind. Yeah, what if we had nitrate? Here's nitrate. So we have, this is now on page 120. Nitrate actually has 3 places where the double bond can go. It can go on the top, it can go on the left, or it can go on the right. Does it really flip around from place to place? No, it doesn't. How would we draw a structure that sort of shows what is happening? So what we would have is we would have our nitrogen, we would have a single bond here, here, and here, and then that red bond would be spread out into 3 places. these two electrons spread out onto 3 places. Question, is this a 1.5 bond? Amna, could you get the door for us, please? Thank you. Is that a 1.5 bond or is it something different? Tell your partner what you think. So basically you have 1 bond spread out over 3 places. So that would be a third. Okay, so this is a 1 1/3 bond. Okay. Okay. So if I were to give you a resonance structure like this, and I said, like, what type of bond do you have? I might give you like multiple choice, you know, and you've got like 1, 1.5, 1, 2, whatever. And I gave you this resonance structure. You should be able to tell me what kind of bond that is. So if it's spread out over 2 places, it's going to be 1.5. If it's spread out over 3 places, it's going to be 1 1/3. What if it were spread out over 4 places? 1 1/4. Okay, so it's pretty straightforward. All right. Which would have shorter sulfur oxygen bonds? SO3 or SO3 2-? That's a really good question. I like that question. What would you have to do to solve this problem? What would step 1 be? I'm going to come closer so I can hear you. Fine. Okay, so we're going to find which element is in the center. But in general, what would we be doing with that? Why would we be finding the element that's in the center? Because we want to draw what? Lewis structures. You cannot solve this problem without drawing the Lewis structures. So draw the Lewis structures. Go for it. Okay? What is step 1? Valence electrons. From our periodic table, how can we tell how many valence electrons in sulfur? There are 6, because we just get rid of that one and we say, oh, there's 6 valence electrons. Excellent. Hopefully you should be getting bored of me saying this stuff by now. Yeah? Oxygen is in the same group. 3 times 6. That gives us 24. Yeah. Is the second one what? Well, we have to find out. Okay. Maybe, but maybe not. Okay, so this one we also have 6 plus 3 times 6. And then If it's 2 negative, are we adding electrons or subtracting electrons? Adding electrons. So that's going to be 24 plus 2 is 26 electrons. Step 2, the skeleton structure should be the same for both. And now we fill up everybody with lone pairs. So everything is the same for these two up till this point. Whoa, those are like way off to the side. I should put those in a better place. Step number 4, count the electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Which one is okay? The SO3 2 minus. Those are the same. And when it's the same, we go to step 6. And in step 6, we ask ourselves, is it an ion? Actually, I should do step 6 down here. Step 6, is it an ion? And the answer is yes. What do we do if it's an ion? Brackets and charge. And then we say step 7, is there any resonance? Are there any multiple bonds? No, you cannot have resonance with only single bonds because you have to have a double bond that could be okay and would be identical in this position or that or the other, okay? So, no resonance. We could check that everybody has 8 electrons. Everybody does have 8 electrons, all right? Now over here, we have to go to step 5 because we have 1 pair too few. One pair too many, sorry. So what do we do when we have 1 pair too many? Erase from the central. Erase 1 pair from central. And we take a lone pair on an outside atom. And we turn it into a bond. Yeah. Okay, so let's take any old one. Doesn't matter which one. Let's grab this one. Here we go. Boom. There we go. All right. I'm going to redraw that down here somewhere. S O O O Then we go to step 6. Is it an ion? Is it an ion? No. Step 7, is there possible resonance? Do we have a double bond that could go somewhere else? Yes. So we're going to have to draw that double-headed arrow. And maybe we could put the double bond on the left. How many lone pairs should that left-hand oxygen have now? 2. And now this one has a single bond. How many lone pairs should it have? 3. 1, 2, 3. And then this one over here would have 1, 2, 3. Are we done? No, why not? There's one more possible place we could put it, so we would have to draw that. I mean, quite frankly, when it comes to the test, I'm probably not going to give you very many resonance structures because they take a long time to draw. Yes? So I won't be giving you like 7 questions about resonance structures. That would be ridiculous. It'll be like 1 or 2. Okay? So now we have S, and we have O, and we have O, and we have O. And then I'll say, oh, here's my final answer. There we go. Yay. Who has longer bonds? What kind of bonds are these ones? These are single bonds. All the bonds in here, what kind of bonds do we have in there? We have 1 and a third bonds. Who's the longest kind of bond? Single, double, or triple? Single is the longest. So if we have 1 and a third, will it be longer or shorter? Shorter. Okay. Yeah. Okay, cool. So anyway, there's a solution here. You've got it already. That's very nice. There we go. We're not going to do that because I think we've already done one like that. Let's take a look at benzene because benzene is important chemically. Okay? This is page 122. Benzene is a 6-carbon ring. Have you guys heard of benzene? Does that sound familiar? Okay. It has 6 carbons and they're in a ring. And they have alternating single, double, single, double, single, double. Single, double, single, double, single, double, single, double, single, double. I cannot speak. Maybe I should have just highlighted the double bond. So we have a double bond. Every other bond is a double bond. And then that would be less messy. Okay, there we go. Can we have resonance here? We could, because we could just move everybody. This guy could move over here, right? This one could move here, and this one could move here. So now we have our double bonds there, there, and there. Is that really what's happening, though? Are they really flipping around? Flippity flip? No. What we really have is we have 3 bonds that can be in, each bond can be in 2 different places. Yeah? So each bond, there's, what am I trying to say? What kind of a bond would this be? Would this be a 1 1/3, a 1 1/2, a 1 1/4? What would it be? Well, if you think about it, half the time this is a double bond and half the time it is a single bond. Yeah? Because you only have 2 resonance structures. So these are all 1 1/2 bonds. And all 6 bond lengths are equal. And what we do often is we will take this 6 carbon ring where we have a carbon at every corner, right? And we had hydrogens on every carbon. But very often, chemists are lazy people. They don't want to draw every single little thing. So they will say, as a chemist, I understand that carbon always needs to have 4 bonds. Yeah? So I can just, and I'm just going to assume that anytime I don't draw a particular bond, there's a hydrogen on the end of it. Okay? So what they do is they say, I'm just going to ignore this hydrogen and assume that other chemists know that there is a hydrogen here. And they also say, well, everything's based on carbon. So if I'm not drawing an oxygen on a corner, that means that this corner right here is a carbon atom. Okay, if I wanted something else there, like let's say I wanted a nitrogen, I would actually put an N. Don't draw that N because there isn't an N there. But if I wanted something other than carbon, I would actually put that atom. But every corner is a carbon. Every corner is a carbon, and the hydrogens are assumed to be there. So we went from having a structure that had carbons and hydrogens drawn in it to having a structure where we've only got lines. Yeah? And we can show the double bond, and we show the double-headed arrow, showing that it goes back and forth in between. But benzene is such a common structure, and if you remember, it's going back and forth between these two. We don't really have a double bond here. What we really have is a 1.5, a 1.5, a 1.5, a 1.5, a 1.5, and a 1.5. And we could draw it like that, but we get so lazy that we're like, why are we bothering with that? Let's just draw a circle, and that circle represents those 3 bonds that are spread out over 6 places. Okay? And I didn't do a very good job of explaining it before. That's 6 bonds spread out over 6 places. That's 3 over 6. That's a half bond. Yeah? So we have each of them is 1.5. Okay? If you're planning on doing anything in chemistry, you are going to come across benzene again and again. Okay? But this is the only time you're going to see it this year, because it's not Chemistry 11, we don't do much organic. Okay? Or at least I don't get around to much organic. If you want organic, I'm sorry, I'm the wrong person. Why is there a number 3 here? That's really weird. Oh well, that's okay. All right, I would like you to take a look on the next page. Each Lewis structure of benzene has 3 carbon-carbon double bonds. Another hydrocarbon containing 3 carbon-carbon double bonds is hexatriene. So here we have our double bond, and our double bond. Do you think that hexatriene will have multiple resonance structures. Will we have resonance for that compound? Think about that. Chat with your neighbor. Why not? Because if you try it, then it's not going to be able to. That's right. Yeah. Yeah. Sure. Yeah, no worries. Yeah. What do you think? Let's vote. Thumbs up, thumbs down, or I don't know yet. Thumbs in the middle. Yes, we're going to get resonance. No, we can't have resonance. Thumbs in the middle. I don't know yet whether we can have resonance. Okay, I got some thumbs up, some thumbs down. I got people not showing their thumbs. Thumbs up, thumbs down, or thumbs in the middle. Pick one. You can be in the middle if you don't know. This is I don't know yet, and that's okay. Okay, we got a lot of both. Now let's think this through. Let's go back to benzene, and you'll notice that we had alternating single, double, single, double. So if I highlight the single bonds, I've got 3 single bonds, 3 double bonds. And this one can move here. This one can move to the next one. This one can move to the next one. Let's see if we can do that same thing with hexatriene, okay? Let's say that I took this bond here and I moved it next door, okay? What that would mean is that we would have a double bond here. Whoa, that was crazy. This would be our bond that moved, okay? Now, if that's the case, we already have 2, 4, 6 electrons for that one carbon. So this carbon here can only have 1 bond on the right. Yes? So what that means is that this bond has to move over to the next one. Okay? So we're now taking this one and moving it over. 1, 2, 3, 4, 5, 6. Okay, so now we've moved this one over here. Okay. And we have a hydrogen here. Good gracious. Now, this bond here, can we still have a double bond there? Can we still have that double bond there? Would that be okay? How many would that give this carbon? How many electrons would that carbon have? How many bonds are attached to the yellow carbon? 5 bonds. Is that okay? 2, 4, 6, 8, 10 electrons. Is it okay for carbon to have 10? No. So this bond would also have to get kicked out. But where does it go? Does it become a lone pair? Because that's the only place it could go. There's nowhere else for it to go. And what happened to the carbon over on the left-hand side? Remember, its double bond, it used to have 2, 4, 6, 8 electrons, but now it only has 2, 4, 6 electrons. So is this a possible, can we have resonance here? No. Yes. Yeah. Okay. This one's quite tricky. If you get it, that's great. If you don't, it's not a big deal. Okay. But it's a nice little thought puzzle to kind of think through. Okay. So the answer is no, it don't work. All right. Did anyone have any questions from the homework, or were we okay? We were okay? All right. Last but not least, we are finishing up this unit. A reminder that our test is going to be next Wednesday, April 23rd. In order to prepare you for that, normally I would give you quizzes, yes, and mark them and get them back to you. This weekend, I will be doing report cards. I ain't got no time to mark nothing, okay? Gonna be writing comments all weekend long. So what I would like to do is I would like to give you a practice quiz tomorrow on calculating average atomic mass. Yes? Do you guys remember how to do that? No. Okay, we'll go over that really quickly today just so we refresh that in your memory. Okay, it's a really easy one, so don't worry. And I might also throw on some ionic Lewis structures. All right, and so that's going to be Wednesday. And then Thursday, we'll again do a little practice quiz, but we'll mark them ourselves in class, okay? They're not 4 marks, but they're for you to see if you know what you're doing. Thursday, we're going to have covalent Lewis structure quiz. But these aren't really quizzes. They're practice quizzes, no marks. Okie smoky? All right. We have one last thing to learn about in terms of covalent Lewis structures. And we have learned about situations where we had... Is that your phone? Oh, AirPods. Okay. Oh. Okay. I don't know what to do with them then. I can hold on to them if that would be best. Pardon me? It's one of your friends. Okay. Can you like text him and tell him we know where his earpods are? Be like, hey, dude, they're in my classroom. Stop pinging it. Okay. All right, so we've got calculating average atomic mass, we've got covalent Lewis quiz, blah, 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 blah. Now we're going to move on and learn the last thing, which is expanded octets. I think he's here. Yep, they've been pinging. They've been beeping along. Oh, you can always just knock on the door and come on in. We're okay. We're okay. All right. So we had incomplete octets. Remember, everybody needs an octet, which is 8 electrons. We had incomplete octets. And the incomplete octets was hydrogen. Who else does not need 8? Beryllium needs 4. Boron needs 6. And aluminum needs not 8. What am I doing? It needs 6. Oh, dear me. 6. Okay. Now we have expanded octets, which means more than 8. Okay? More than 8 electrons. This can only happen if you are in row 3 or lower on the periodic table. Okay? on the periodic table. So if we go look at our periodic table, get rid of all this. We have helium is in row 1. This is row 2. This is row 3. So if I said to you, can carbon have more than 8 electrons? Is that allowed? It's in row 2, so the answer is no. You have to be in row 3 or lower to have more than 8 electrons. So carbon is no, fluorine is no, nitrogen is no, oxygen is no, neither is boron. Okay, none of those can have more than 8 electrons. However, when we get down to phosphorus, phosphorus is in row 3. So yes, it can have more than 8. It still usually has 8, but sometimes it can have more. So if we're like, oh my gosh, I've got this extra pair of electrons, where do I put them? You could throw them onto phosphorus, right? If you're like, I've got a structure, it's supposed to have 28 electrons, but it only has 26, throw the extra ones onto your central row 3 or lower atom. Okay, so that's going to be phosphorus, sulfur, chlorine, bromine, and we even get into things like krypton and argon. They're weird because they can have more than 8, right? So even though they have a complete octet, we can chuck more onto a noble gas. Really bizarre stuff, okay? So all of those ones, usually those are the ones we're going to see. You could have argon, but it's pretty small. It doesn't tend to do it, okay? So let's look at some examples of how this works. Okay. Oops. There we go. So here we have PF5. Do you guys remember anything about fluorine and how it bonds? Fluorine can have how many bonds? If you don't know, draw yourself the Lewis structure for just the fluorine atom. How many valence electrons on fluorine? Fluorine is group 17, so it has 7. So we have 1, 2, 3, 4, 5, 6, 7. We have 1 gap. Therefore, how many bonds can fluorine form? 1 bond. And it is not in row 3 or lower, so it cannot form more. Okay? Fluorine is only ever 1 bond. So it's not like we could say P, F, F. Like that would be not okay because that fluorine right there would have 2 bonds and that is a no-no. Okay? So what do we have to do? Well, everybody has to attach to the phosphorus. So we'll stick them on there as best we can. I mean, if you didn't know what you were doing, you could probably just be like, if I were to just draw it down at the bottom here, I would go P, and I'd be like F, 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 fluorine, 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 fluorine. And I'd be like, oh, dang, there's another fluorine. You can just have it sticking out to the side. That's okay. All right? We're not going to worry too much about the actual shapes. Okay? And then, of course, everybody would have its electrons filled up. Okay, I'm not going to draw them all because they're all up here. Okay? And let's see if our actual number of electrons works out. P has 5 valence electrons. Fluorine, we have 5 times 5. That can't be right. 7, 5 times 7. Sorry. Yeah, that's better. And that's going to give us 40 valence electrons. Does our structure have 40 valence electrons? Well, you go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. Oh, hey, look at that. Yes? Every single fluorine has 8 electrons because everybody's supposed to have 8 electrons. The only one that's kind of weird here is the P. And you say, well, P has 2, 4, 6, 8, 10. And normally that would be bad. But because phosphorus is in the middle and because it is in row 3 or lower, we can do that. We are allowed to do it. But it's unusual, and don't be trying to have 10 electrons around things on a regular basis. Again, this is going to be like maybe 1 or 2 questions, okay, on your test. All right. And what you'll see is like things like SF4. You'll see sulfur, that's in row 3. You'll see I, which is in row 5. Okay? So those are okay to have more than more than 8 electrons. On the other hand, N and O, these are row 2. Are those okay to have more than 8 electrons? Okay, so we can't do that. Alrighty. If you're interested in why, it's just because the atoms, as you go down the periodic table, you have more and more shells. So the bonding takes place at a larger distance from the nucleus. And so you can kind of just, if you imagine, if you've got something small, you can only probably fit 4 things on it. But if you have something big, you can kind of, stick more things around it just because it's larger. Okay? All right, I would like you to try SCl6, and we're going to do it exactly the same way we did our other structures. We're going to count our valence electrons. Draw a skeleton. Again, you're going to be looking for who is your central atom. Sulfur has 6. Chlorine has 7, and we've got 6 of them. 6 times 7 is 42, plus 6 is 48. And once you get to this point, you should say, oh no, I've got one thing on every side. What shall I do? Just throw them onto sulfur because sulfur is in row 3 or below. So just put them anywhere you want to. You can put them here. You can put it here. Okay, just give yourself enough room to draw all the dots. And in fact, for structures like these, because the dots get really messy, if you would like to, instead of drawing dots, if you would just like to say, that's 2 dots, 2 dots, 2 dots, you may do so. Isn't that nice? But you should always make sure they're like up and down, left to right. Because this is a lot of dots here, right? And one of those little ones is equal to 2 dots. One of those little ones is equivalent to 2 dots. Yeah. Step 3, add lone pair. Step 4, count the electrons. Well, we have 3 lone pairs on every chlorine, and there are 1, 2, 3, 4, 5, 6 chlorines. 6 chlorines with 3 lone pairs each gives us, and a lone pair is 3 times 2, which is 6. And 6 times 6 equals 36. So we have 36 electrons, and then we have the ones in the bonds, 36, 38, 40, 42, 44, 46, 48 electrons. And guess what? It's correct. Yes? You'll find that most of the time you're just like, oh, well, that worked out. Try ClF3. Who has to go in the middle? Normally we would say chlorine, which has 7 valence electrons and has 1 gap. Normally, chlorine forms only 1 bond. But who's our other choice? Who else could be in the middle? Fluorine? Fluorine only ever forms 1 bond. There's no exceptions. Nothing else. So that means chlorine is our only option. Has to go in the middle. So we have 7 valence electrons. 3 times 7. That gives us 28 electrons. Cl has to go in the middle. We don't have a choice. We have 3 fluorines. Fluorine, fluorine, fluorine. There's not enough atoms here for me to say, yeah, just go ahead and draw the line. So let's use dots. So let's fill everybody up with lone pairs. What is happening? Stop doing that. There we go. Okay. So we've done steps 1, 2, 3. Valence electrons, 28. Skeleton structure, put Cl in the middle. No other choice. Step number 3, fill up everybody so everybody has 8 electrons. What's step 4? Count. How many electrons in this structure? We have 26 electrons. Ooh, this is a new one. We have 1 pair too few. We've been used to having too many, but here we have 1 pair too few. So instead of erasing a pair from the central atom, we will add a pair to the central atom. And that's going to require, in this case, I'm going to erase this pair so I can redraw it so it's a little bit tidier. I'm going to draw a pair over here and a pair over here. Although, if you had wanted to, you actually could have a pair here. And if you wanted to draw the other pair down there, that would be okay. Yeah? As long as you just put them somewhere where it's obvious that they are on the chlorine. Is good? How about you guys try ICl4 minus? Mm-hmm. Yeah.
My ingredient, is it good enough? Is there still time that I can get it up by 2 at least like 75? So?
Probably not.
Probably not. Yeah. Everything like this. Have you ever seen my video?
Mm-hmm, but I need to do it on here so I can do it after work because we don't want it projecting all over. Okay, let's try ICl4. Okay. Did you guys get this far? Yeah? And now we look at our electrons and we say we should have 36, but we only have 32. We have 2 pairs too few. Where do we put them? We put them on the central atom. Okay, so I'm just going to put them kind of like on a diagonal here and here. If you tend to be a very messy drawer, this is not the time to be messy. Take a little extra time, okay? It doesn't have to be super tidy. It just has to be like, I have to be able to see that those belong to the eye. Question? Oh, like... Okay, the question is, are we allowed to do this? And the answer is no, we never have unpaired electrons in molecules. There's only unpaired electrons in individual atoms. Okay, they always have to be paired up. You either have a bonding pair or a lone pair. Okay, good question. Okay, and now we have to say to ourselves, oh my gosh, step 6, is it an ion? Yes, it is. So we need brackets and a charge. Okay, is there any resonance there? No, there's no double bonds. Okay, so we're done. So what you could do is, for practice on these, you could do, where did they go? You could try the example 4, and then do 1, 2, 3, 4, 5. Okay? Yeah. That's the lesson, unless you guys want a little review of how to calculate average atomic mass. Do you want a quick review on that? Yeah, okay. All right. Ooh, average atomic mass. So what you're going to do is you're going to say, if I want to find the average atomic mass, I'm going to take the decimal percent of isotope A So I have isotope A and I have isotope B. Yeah? Is this sounding familiar? Okay. I'm going to take the decimal percent of isotope A. And so if I had 96%, the decimal percent is 0.96. Yeah? That's how decimal percents work. Yes? Okay. And we're going to multiply that by the mass of isotope A. We're then going to add that to the decimal percent of isotope B times the mass of isotope B. And we could, if we wanted to, if we had a third isotope, we would take the decimal percent of isotope C and multiply by the mass of isotope C. Do we remember this? Is this ringing bells? Yeah? Okay. So extra practice on that would be, let me find the page here for you. Table of contents, average atomic mass. So there are some questions in section 3.3C and 3.3D. Okay? If you're interested in the enriched stuff, that's 3.3C, but that is optional. Okay, so the quiz tomorrow is going to include (3.3C), 3.3D, and 3.5B. So you will want to go back and take a look at ionic compounds. And remember, when I say quiz, is it for marks? No, because you're going to be marking either your own, or if you have a good friend, you can swap with them. Like if you're comfortable swapping with someone, because sometimes it's nice to see what somebody else has done, or it's nice to be able to see, oh, maybe I can see what I did wrong, or I can see what they did wrong, so I won't do that in the future. But if you're not comfortable doing that, you can mark your own. Okay, we'll go over them together. Okay. So what you should be doing then right now is you could work through any of 3.3C, 3.3D, 3.5B, just to remind yourselves of how those questions go. None of them are particularly difficult, but you'll want to do at least a couple questions from each to kind of refresh your memory. Okay? And that's the lesson. Yep.